The sunlight hitting your face right now took 8 minutes to cross the vacuum of space, but its journey began long before that. This light is actually an ancient relic of the deep past. The sun has no fixed solid surface. The temperatures are so extreme that no solid or liquid can exist. The entire structure is composed of gaseous atoms and plasma. This 4-panel diagram tracks the chronological stages of the solar system's formation. About 4.5 billion years ago, a solar nebula of gas and dust collapsed under its own gravity, spinning and flattening into a disk-like structure. At the center of this disk, material clumped together into a protostar. Over tens of millions of years, gravity forced the internal temperature and pressure to rise until it triggered the fusion of hydrogen. To understand how this 4.5 billion-year-old machine operates, we have to travel to its exact center and follow a single particle of energy trying to escape the crush of gravity. The sun's core is an environment of unimaginable pressure. Here, the density is 100 times that of water, and the temperature reaches at least 15 million Kelvin. This diagram illustrates the proton-proton chain driving the sun's energy. 4 hydrogen nuclei are crushed to produce a single helium nucleus, positrons, neutrinos, and gamma rays. This conversion is imperfect. The resulting helium nucleus weighs 0.7% less than the 4 original protons. This missing mass is converted into pure energy in the form of gamma rays, a direct application of Einstein's E equals mc squared. This microscopic, continuous atomic conversion is the only engine pushing outward against gravity, preventing the star from collapsing under its own weight. Once created, the energy enters the radiative zone. In this layer, the density is so high that light cannot travel in a straight line. A photon can only travel about 10 centimeters before it is absorbed and scattered by a local atom. It bounces in a random direction, a process known as a random walk. Because of this constant scattering, it takes between 10,000 and 170,000 years for a single photon to finally reach the edge of this zone. At the interface layer, the rotation of the sun shifts. The inner radiative region rotates uniformly, while the outer convective region rotates at different speeds, creating shear flows that generate the sun's magnetic dynamo. As the energy enters the convection zone, the plasma becomes opaque, trapping heat. This trapped energy makes the fluid unstable, causing it to physically boil and rise toward the surface in massive currents. The energy's escape has changed from a microscopic 1,000-year pinball game into a massive, boiling elevator ride straight to the surface. This textured surface is the photosphere, a layer only 100 kilometers thick. This is the deepest part of the sun we can observe with visible light. The energy continues into the chromosphere, the sun's lower atmosphere, where it rides along tangled and twisted magnetic field lines. These incredible magnetic fields can trap cooler plasma, forming massive glowing loop structures that are called prominences. These prominences can persist in the corona for months, looping hundreds of thousands of kilometers into space before they become unstable and burst. While the sun appears as a calm, glowing orb from Earth, its surface is a violently tangled, magnetically unstable environment in constant motion. Surrounding the star is the corona, a vast aura of plasma that extends millions of kilometers into space. The corona presents a massive scientific mystery. Its temperature is in excess of 1 million Kelvin, making it significantly hotter than the surface layers directly beneath it. To measure solar activity and energy output, NASA and the ESA have launched orbiting observatories to photograph the corona and study the solar wind. In 2018, NASA launched the Parker Solar Probe to travel directly through the sun's atmosphere. It is currently measuring the star's magnetic fields from a distance of just 6.5 million kilometers. The sun is an active, breathing nuclear dynamo currently halfway through its lifespan. It dictates the environment of our entire solar system.